Feeling that week 7 exam pressure? Hey, don't worry, I've got your back. This is going to be your complete guide to absolutely nailing supervised learning and regression. We're going to break down all the theory, piece by piece, and then walk through the entire lab step by step. By the time we're done here, you are going to be so ready for that test.
All right, so here's our game plan. We're going to start with the why we even use regression in the first place. Then we'll roll up our sleeves and actually build a price predictor using the classic California housing data. After that, we'll check out a really cool alternative called decision trees. Learn how to tell if our models are any good, and then we'll wrap it all up with a super fast review to make sure it all sticks. Let's do this.
Okay, first things first, let's get to the heart of it. What is the main problem that regression is actually designed to solve?
This is the core question, right? It could be the price of a house, what the temperature will be tomorrow, or even a stock price. We need some kind of tool that can look at past information and predict a specific number, not just, a simple category. And that tool is regression.
Now listen up, because for your exam, this is absolutely critical. In supervised learning, it all comes down to your goal. If you're trying to predict a number that can be anything along a scale, like a price of $100,000 or a temperature of 75.5 degrees, you're doing regression. But if you're trying to predict a label, like spam or not spam, that's classification. Totally different tools for totally different jobs.
So, how do we actually do it? How do we make these predictions? Well, let's start with the first and most fundamental tool in our toolbox, linear regression. At the heart of linear regression is this one simple-looking equation. But don't let its simplicity fool you. It's incredibly powerful. You can think of it like a recipe. The X's are your ingredients, things like the size of a house or its age. The model just follows this recipe to combine them and cook up the final prediction, which is Y.
Okay, so let's break that down, because this is the important part. The intercept, B, that's just our starting point. It's a baseline value before we look at any of the house's features. Then each feature gets a coefficient, a W, which acts like a volume knob. A big positive knob for, say, square footage cranks the price way up. A negative knob for being far from the city, well, that turns the price down. The entire goal of the model is to find the absolute perfect settings for all these knobs to get as close as possible to the real prices.
All right, enough with the theory. Theory is great, but let's see how this actually works in the real world. We are going to walk through the entire California housing lab, step by step, just like you'll see on the exam.
We'll be working with the California housing dataset. It's a classic. It has data on over 20,000 neighborhoods, and for each one, we have 8 features, like the median income and the average age of the houses. Our one and only goal is to use those 8 features to predict the median house value.
First things first, we got to load the data. You can think of this whole phase as being a detective. You're just gathering clues, getting a feel for the dataset. We'll check its description, its size, the names of all the features. Basically, we want to know exactly what we're dealing with.
Okay, next up, we'll pop the data into what's called a pandas data frame. It's basically like putting it into a super-powered spreadsheet. This makes it really easy to get a quick statistical summary. And here's a little pro tip. To make things run way faster while we're just experimenting, we'll create a tiny 10% sample. It's a great trick for getting things done quickly.
Now, this is where the real prep work begins, and this part is so important. First, we separate our features from our target value. Then, and this is key, we do a train test split. We hold back 20% of our data. Why? Well, we don't want our model to cheat. It trains on one set of data, and then we test it on a different set it's never ever seen. Finally, we scale the features. This just makes sure that features with really big numbers, like population, don't overpower the ones with smaller numbers. It's all about making it a fair fight.
With all our data prepped and ready to go, it's time for the magic. We feed our training data to the linear regression model. It goes to work, crunches all the numbers, and learns the best possible values for all those volume knobs, the coefficients, and that baseline intercept. Once it's done training, we can just pull those learned values right out of the model.
And check this out. This is what the model actually learned. By plotting those coefficients, we can instantly see what features it thinks are the most important. And it's no surprise, right? Median income has the biggest positive impact, but what's really cool is that latitude has a big negative impact. Our model figured out all on its own that generally the further north you go in California, the lower the house price. Pretty smart. Finally, it's the moment of truth. We take our trained model and ask it to make predictions on that test data it's never seen. Then we measure how well it did, and we make a simple plot to see it with our own eyes. This visual check is so powerful. Basically, the closer all those dots are to that perfect diagonal line, the more accurate our model is. It's that simple.
So our linear model is pretty powerful, but it makes one huge assumption, that all the relationships in the data are nice, straight lines. But what if they're not? I mean, what if the real patterns are way more complicated? For that, we need to turn to a fantastic alternative, the decision tree.
A decision tree works just like you're playing a game of 20 questions. It starts by asking a simple yes or no question about a feature. Something like, is the median income less than 3? Based on the answer, it splits the data down one of two branches. And then it just does that again and again and again until it finally gets to a prediction at the very end. It's an awesome way to capture those messy, real-world patterns.
So, how does the tree know what question to ask? How does it pick the best split? For regression, it's all about one key idea: variance reduction. The tree's goal is to ask a question that creates new groups where the house prices inside each group are as similar to each other as possible. A great split is one that takes a really messy, spread-out group of prices and turns it into two much cleaner, more consistent groups.
For instance, let's say before we make a split, the variance of the house prices in our current group is 25.67. That's pretty high. It just means the prices are all over the map, which makes it super hard to make one good prediction for everyone in that group. But look what happens after we ask a really smart question. The combined variance of our two new groups plummets all the way down to just 0.67. The total variance reduction is 25%. I mean, that's a massive improvement. And that tells the algorithm, yes, that was an amazing split. Keep it and move on to the next one. Now, real quick, while we're talking about decision trees, you should know they're also amazing for classification. In that case, instead of reducing variance, the goal is to reduce something called impurity. A really common way to measure that is with the Gini index. Just like we see here, we calculate a weighted Gini score to find the best split. It's the exact same idea. Find the question that creates the purest, most consistent groups you possibly can.
So we've built a couple different models now, but how do we formally measure their performance? How do we keep score and declare a winner? Well, that's where our evaluation metrics come into play.
You absolutely 100% need to know these three for the exam. MAE, mean absolute error, tells you, on average, how many dollars off your predictions are. RMSE is similar, but it punishes big mistakes way more harshly. And my personal favorite, the R-squared score, tells you what percentage of the price variation your model actually understood and captured. A score of 1.0 is like a perfect crystal ball, while a score of 0 means your model is basically useless.
All right, let's bring it all home. We're going to do a rapid-fire review of all the most important concepts just to lock them in your brain for the exam.
Here they are. This is your essential vocabulary list. Just make sure you can comfortably explain what each of these things is, from why we do a train test split to what an R-squared score actually means. Think of this as your personal study checklist.
And here it is, your practical roadmap. This is the complete workflow we followed in the lab. And this isn't just for the exam. This is your battle plan for basically any regression problem you'll ever face. You explore the data, you prepare it, you train a model, and you evaluate how it did.
So, with these tools, you're not just analyzing data anymore. You're actually building models that can predict the future. So the final question is, what are you going to predict next? Now go crush that exam.